Hey everybody, it's John here. So in this video, I'm going to talk about some applications, and then we're going to bring a new number into the mix that's very relevant to applications. But talking about bacterial growth, so Louis Pasteur noticed that a certain culture of bacteria in milk doubles every hour. So here's the model that we come up with, which makes sense. So in the 0th hour, 2 to the 0 is 1. So there were 2,000 bacteria to begin with, which actually answers my initial question. Okay. Oops. So this number is the initial value. This is the rate at which we're growing, so we're doubling every hour. So when I plug 1 into here for hours, I should have twice as many as I did the previous hour. So 2,000 times 2 gives me 4,000. And then if I double it again, that's times another 2, which works as an exponent. Okay, if I just keep repeatedly multiplying by 2, that's how exponents work. 2 times 2 times 2 is 2 to the third. So after 3 hours, I'm multiplying the initial amount by 8. So after 10 hours, I'm really just looking for b of 10. I'm going to plug 10 in for t. So 2 to the 10, I'm using my calculator here. 2 to the 10 is 1,024 times the 2,000 that was there, gives me 2,048,000 bacteria. Okay. And just a fun fact, the singular of bacteria is bacterium, but you almost never have a single bacterium. And so we almost always just say bacteria because it's always more than one. So that's a lot of bacteria after 10 hours. So now we want to know the time when the number of bacteria will be 32,000. So 32,000 equals 2,000 times 2 to the t. We're looking for t. So I can estimate this right now, but what this question gets to the heart of is the need to be able to solve for the exponent. And that need is where logarithms come in. And that's what we're going to talk about next week. We're going to talk about logarithms and then how we use them to solve exponential equations. So I can divide both sides by 2,000, and 32,000 divided by 2,000 is 16. Okay. Now in this particular problem, I am seeing that I can turn 16 into 2 to the 4th. 2 times 2 is 4, times 2 is 8, times 2 is 16. And so this calls back to that problem we did earlier, where if the bases are the same, that means the exponents have to be the same. So t equals 4. So it's going to take 4 hours for the bacteria to be at 32,000. But let's say this number didn't come out to be something that was 2 to some power evenly. If this had come out to be 15 instead, I would know that my answer is somewhere between 3 and 4 because 2 to the third is 8 and 2 to the 4 is 16. And I would think it would be closer to 4 than it would be to 3, but I wouldn't know the exact value unless I brought in logarithms. And that's what we're going to learn about next week. All right. So this is a great example. This is very simple. This is doubling. Half-life examples with radioactive materials are very similar in that fact that you're multiplying by 1/2 over and over again, so that's an exponential. But the real number that as a base that helps us deal with natural processes in the world is called the natural base. And so what we have here, I don't know if you guys are familiar with the exponential compound interest function. So if you have a certain amount of money that you start with, let's call it a principal, P, and you put it in a savings account that earns a certain interest rate that's compounded a certain number of times every year, this is the formula that you would use, where T is in years and N is the number of times it's compounded. And you can see there's a little bit of a, if you ignore the R here and just focus on the N's, you have this 1 plus 1 over N to the N power sort of creeping in here. And so that's why I bring up this exponential compound interest formula. We can also just put this into y1 on our calculator like we did with the rational functions when we were testing those out. So I'm going to do 1 plus 1 divided by x, close the parentheses, raised to the x. I'm going to graph it, but I'm not even really interested in the graph. I am interested in the table of values. So last time we set up so that we can put in whatever values we want. And it's funny, I already have, on my calculator, I already seem to have these values in there. So 1, 2, when I plug in 2, I get 2.25. When I plug in 10, I get 2.5937. When I plug in 100, I get 2.7048. When I plug in 1,000, I get 2.7169. When I plug in 10,000, I get 2.7181. When I plug in 100,000, I get 2.7183. And so you can see that the numbers change considerably from here to here and here to here and here to here. But now it looks like the 2.7 is stuck, and these numbers are getting closer and closer to a certain value. That value is E, 2.718281828, and it seems like it repeats, but it doesn't. It's irrational, 459045. It keeps going forever, non-terminating, non-repeating. So there's a ... here. And you can find this number on your calculator, just like pi. And it's actually right underneath pi. If you hit second divide, you get your E number, and your calculator, if you hit enter, your calculator will spit out 2.718281828. And it does seem like it's repeating, but there is this non-repeating part that takes place. Okay, so in the next video, what we're going to do is we're going to do some transformations on your natural exponential function, which again, I'm going to do that very quickly because I'm not that worried about graphing. What we need to remember is what the base means here. And then we're going to do a couple more application problems, and then that's it. All right, so I'll see you in the next video.